All right. Well, hi everybody. I'm Ryan. I'm an instructor, P2 instructor for FlyLife Paragliding up here in Bozeman, Montana. And then outside of that, I'm a PhD student at Montana State University. I study mechanical engineering with a research focus in flexible wing aerodynamics. I look a lot at insect wings. So this is a computational fluid dynamics model showing our flapping motion on an insect wing. You're not seeing the fluid flow around it right now, but just kind of a little view on what I'm looking at, mostly at hawk moths and honeybees. A lot of this research is going to go into small scale robotics. So we're looking at drones on kind of millimeter size scales. And the big thing that I work on is incorporating these elastic bending models into the fluid dynamics model. So it looks at both the structure and the fluid flow. That's why in this particular video, you can see that plate bending back. So now I'm trying to integrate those sorts of things into our flapping wing model, and then develop fast ways to solve for forces on those wings so that we can make some smarter decisions about how we design some of the artificial wings to be used in small-scale drones. So anyway, enough about me, a little bit on aerodynamics. So with these classes, I'm going to start at as basic of a scale as I can, and then kind of move into some of the more hard sciencey stuff, and we will just see how it goes. If you guys have questions at any point, feel free to come out of mute and just chime in whenever. I won't be able to see if you post a chat or anything else like that, so just feel free to chime in. You'll come up on my end. Also, for those of you who have been following along, we have a couple of our recordings. This one's currently being recorded, and we're getting those posted onto YouTube. Sounds like we just got the first one. I need to do a couple updates on my video from last week on airspace regulations, and then we'll get that one posted as well. So stay tuned for that. I'll be sure to post everywhere that I've been posting about these classes. Okay, so aerodynamics. Why and how your wing flies and why that matters. So to start off, we'll talk a little bit about air pressure. And kind of what it means to be at high and low pressure. So the basic idea to understand pressure is we think of squeezing and pulling on things. So for example, if I had this little box and inside of each of these X's is a little air molecule, I can pull this thing out. That would be like a low pressure. It'd be like putting your hand on the end of a vacuum, that sort of a thing. That's kind of a low pressure situation. On the other hand, if I squeezed on this box really hard, that would create a high pressure. I can think of that as like as you crack the can on a soda, how air starts to escape out the top. Or even just if you had like a water bottle with some air in it and you squeezed it really hard, you can feel that pressure build up just from squeezing it in your hand. So with that, why is pressure important? Well, the air around us has mass. In other words, it weighs something. And that means that gravity of Earth pulls it down. And so it's constantly under some amount of pressure. So that kind of baseline pressure is called gauge pressure. And high and low pressure is referenced from that. So to have zero pressure would be like the vacuum of space, would be like a zero pressure situation. And that's not what we're talking about. We're just talking about higher or lower than kind of what's the standard pressure of the air around us like right now. Cool. So if we look at our paragliding wing, I've got a little graphic up here. And if we were to cut this thing along the chord, so if we were to cut along this line, we end up seeing this shape that we call an airfoil. That's maybe a bad one. Or something like that. So what we have with that is out here in front would be our leading edge. So the part of the wing that's penetrating forward into the air. On the back here would be our trailing edge, where our brake lines are connected. And we'd have lines scattered across the wing, A's, B's, C's, maybe D's, depending on the wing. This is our basic airfoil shape. And the reason that this is important is this is actually what's generating a force that's pushing up to contradict gravity that's pulling you down. So if we look at how that kind of works, there's like a few different theories that have been thrown out over the years. And maybe a good place to start with this is to talk about why some of those theories are not quite as relevant, even though I'm sure many of us have heard about them. First one being Bernoulli's principle and how that applies to our airfoil. The Bernoulli's principle is really just a balance of kinetic and potential energy. And it all results in this equation that's basically, out in front here we have our velocity, which is squared. That's velocity of the air, or in our case, our wing velocity, which makes up that velocity of the air. We have gravity times our height. Sorry, was somebody chiming in there? And then next to that, we have our air pressure that we just talked about, and our fluid density. In this case, our fluid is air, and our air density is relatively constant. Granted, it does change slightly as you move, let's say, up in altitude, or under different pressure conditions, you might have a slightly different air density. But the basic idea is that the sum, so when you add these all together, the result is going to be constant along a particular streamline of air. Streamline of air means that it's the path that air would take if it were in perfectly laminar flow, and it's not across that path. So in other words, what does that look like on our airfoil? The basic idea here is, let's say we had 2 points out in front, and our wing is flying into those 2 points, right? So we'll look at this as if we're traveling along with the wing and what the air does around it. So as the wing comes into these pieces of air, it's going to move up, over, and then down the backside of the wing, or under, depending on which particle of air we're looking at here. So the idea behind Bernoulli's principle is that this distance along the top surface of the wing is actually a little bit longer than this distance down here on the bottom of the wing. And then the whole idea behind the Bernoulli's principle is that these two air particles would separate here on the leading edge, and then they would come back together on the trailing edge. So with that, what you would look at is this particle on top is moving a longer distance than the particle on bottom, but they're getting to the same point at the same time, meaning that the particle on top is moving faster. Now, before I continue, remember, this is not the correct way to look at these airfoils, because as more testing on these airfoils was performed, we found that these particles at the trailing edge here do not have to come together. And in fact, the particle on top actually ends up much faster than the particle on the bottom, and so they don't ever reline again. But if they were to line back up, you'd be looking at an increased speed on the top here, which means that our velocity here would be going up. And in order for our velocity to go up, we assume almost no change in that vertical position, z. So instead, we have to counteract that with our pressure in order to keep this equation constant, which means that our pressure goes down. If we had low pressure on the top, low pressure, and then we had high pressure down here on the bottom, again, we think about like opening a soda can. From the high pressure, that fluid's going to want to be forced out into the low pressure, meaning that you'd have a net force going up through the wing, generating lift. Now, like I said, these particles at the trailing edge here don't line up, so this technically doesn't work. I mean, for all intents and purposes for our paragliding, maybe it's not super relevant that we're worried about that, but let's dive a little bit deeper into this and see just why our paragliders are flying the way that they're flying. So if we look at, instead of the Bernoulli's principle, let's look at the CoWanda effect and what that means. The CoWanda effect is essentially the tendency of any fluid to follow the geometry along which it's flowing. In other words, CoWanda effect of fluid moving across just a shelf that drops, it would fall down and then realign with the solid, as we can imagine. You can imagine this as water or air. However, there are limits to the CoWanda effect, where in this case, you probably have some amount of separation away from the wall here, while something, well, a geometry, solid geometry, that maybe flowed a little bit better like that, you'd have your fluid constantly following that flow. And you can imagine this as, let's say, a top-down view on this rather than looking at it from the side. So this isn't being pulled by gravity, instead this is a driven flow that's just kind of following the geometry that's alongside it. Now, the reason it wants to do that is you can imagine that as this fluid is getting kind of extending out away from this shelf, it's kind of pulling away from that shelf, meaning, like we said with our pressure earlier, if we're pulling that away, we're looking at a low pressure region, which is going to bend it back down. Kind of a rough idea on the CoWanda effect. It's not all driven by pressure, but we won't get into too much of that. The main idea is just that fluid, any liquid or gas, has a tendency to follow that geometry that it's moving along. Cool. So now, the second big consideration here, and this one's a bit more difficult to grasp, I'll say. But basically, if you have any flow that's curving, the inside of that curve, right? You can imagine that if this flow is curving around a big circle, it's a big circle down here. So the inside of that circle, in other words, would be the inside of the flow. The main idea is that the inside of the turn is going to have a lower pressure than the outside of the turn. Now we can imagine this, like I mentioned up here, with this kind of shelf situation. As this flow is turning down, this is now the inside of the turn. We have this low pressure. We can also think about this if we were to look at flow in a pipe. We had flow in a pipe that then turned down. We would see that as this fluid moved along the pipe and it started to come down here, you can imagine how that fluid's going to kind of hit this wall and build up this higher pressure region on the outside. Well, on the inside, it's pulling away from the wall a little bit and building up this lower pressure region. Now, the interesting thing is you don't necessarily need pipes or walls in order for this high to low pressure gradient to be there. You just need turn in your flow. So now let's look again at our airfoil. Flow is coming in, moving over the top, and then shooting down. We'll draw that in a little bit nicer. Coming down, while on the bottom, seeing the bottom surface and then coming down, right? So now if we look at, again, this kind of inside of the turn versus outside the turn, and we see this upper surface, we see the inside of the turn is where the wing is. This is the inside, whereas the outside is up here on top, away from the wing. On the other hand, if we look at the bottom surface, you can see it especially more toward the trailing edge, but this whole thing is a little bit curved down. And so the inside is actually down here, away from the wing, while the outside of that turn radius is in close to the wing. So again, low pressure is going to be the inside of that turn radius. So what does that mean? That means we have this kind of low pressure down here. And as we move away from the wing, that pressure gets larger out here. Where on the bottom surface, we start with this really high pressure. But as we move away from the wing and toward the inside of the flow's turn radius, that pressure is actually decreasing. I hope that visual kind of helps with that idea. But in any case, all this results in high pressure on the bottom, high pressure, and low pressure up on the top of the wing. And as I mentioned, any flow really likes to move from high pressure to low pressure, so that results in this net force pushing up through the wing. Cool. Any questions so far? No, I'm kind of screaming through a little bit of this. All right, so now let's look at this wing again and see how that pressure is kind of distributed across the surface. So as the wing's kind of moving this direction, we're going to end up with kind of this blunt body object. Think about anything that you're throwing through the air. It's going to be pushing air a bit right in the front, right? So this is actually going to have a little bit of a high pressure right here on the nose. But that pressure is only going to be limited to right there on the tip. And then outside of that, this is where we see this low pressure. It starts pulling air kind of away from the wing along the whole top surface. This is where you'll end up seeing some of these plots. They'll have a line around this. It has these kind of weird bubbly bulges going on. Now if we look again at the bottom surface, there is actually this really weird little low pressure region. But then we're going to see high pressure, so in other words pushing in on the wing, along most of the bottom surface, and that's going to be not quite as dramatic of a shift in how much of a pressure change there is. It's going to be a more kind of laminar, uniform, high pressure along the bottom surface. What all that results in is this net force, and you can see kind of how this green region is a little bit on the leading edge side of the wing. It results in this net force that's going to come out at this angle. Now with that, we have two components here. We have a lift force, which is going straight up and away from us, the paraglider, who's down here. We'll draw ourselves in as a grape. And then, in addition to that lift force that's pulling us up, we also have this forward force that we can think of as a thrust. And so this is why different wings can fly faster, is they change kind of this ratio of lift and thrust, and of course drag, which is what's kind of pulling this wing back. We also have a drag force going, well, to make it a true drag force, it's coming straight back away from lift. And so this is kind of where we start to see differences in these different wings. They have more lift, they have more of this kind of perceived thrust, maybe they have less drag. Cool. Any questions on this right now so far? We'll keep pushing along.
Hopefully we can figure out.
So the next big component in all this whole fun and games is kind of what happens with your change in angle of attack. Let's look at angle of attack really quick. I'm never going to be good at drawing airfoils, but that's okay. So if this is our paragliding wing again, we're looking at it again from the side. We know that it's kind of moving at this angle, right? It's moving down a bit because of our weight and forward from the thrust component of that lift. And then it's not moving down super fast because we have that lift force as well. What that means is that we have flow coming in toward the wing from the kind of opposite direction of how we're moving. So now if we wanted to start drawing some lines, let's look at a line from the leading edge through the trailing edge, and we'll pretend that's straight. We'll have another line that's kind of parallel to our direction of travel or our direction of airflow. What does that look like? So in between here, this is actually our angle of attack. Now on like airplanes, you might not have the same angle of attack, and it's a little bit easier to draw because airplanes are usually flying forward rather than down at an angle. So just know if you see that angle of attack coming from a horizontal, that entails that you have horizontal motion, which we usually don't as paragliders. That's why I'm drawing it in this way. So cool, angle of attack. We're looking again at kind of this, we'll call it a base case of our wing. Right, we have that lift force coming out like this. Now what happens if we change our angle of attack so that it's a lot more dramatic? Something, let's say, like this. Now we still have motion going at that downward angle. Again, is going to be this line. Color do that purple. And then we look at our line from trailing edge to leading edge. Now this angle of attack is going to be a lot larger than the angle of attack up on top here. And what we see with our lift force is that it's going to follow the shape of the wing, not follow the orientation relative to Earth. So if we imagine just rotating this up, this first wing that we drew, now our lift force is kind of looking more like this, right? where we have a much larger lift component. Because again, this kind of lift versus thrust is more oriented compared to us, a much smaller thrust. The reason this is particularly important is a lot of times you talk about speed to fly or MinSync or different things like that. This is kind of the thing that we're playing with, is this angle of attack and how we're changing our relative lift versus thrust out of that lift force. Again, this purple arrow being the aerodynamically speaking lift force, while this kind of perceived lift and thrust are these two components of that. So for those of you who maybe haven't been flying much or haven't flown yet, we can change our angle of attack with our brakes. Brakes are hooked up to the back of the wing out here, and so pulling down on these brakes, that's how we're going to end up with this new angle of attack. Now, this isn't an exact science, especially in paragliding where these wings are flexible. All of the data I've seen, like released from paragliding manufacturers, I'll use rigid airfoils, which means that we're looking at these airfoils exactly how I drew them. But when we look at a flexible airfoil, instead of that big dramatic change that I drew, again, someday I'll be able to draw an airfoil. So instead of having this perfect rotation, we're actually going to see this kind of full change in camber to the wing, where we can see this kind of big inner curvature as we pull down on the brakes. And so that actually changes the type of airfoil that we're dealing with. So right now in pretty much all aerodynamics, coefficients of lift, in other words, the amount of lift that a wing sees, is dependent on the wing's shape. And that wing shape, a big part of it is this camber, this curvature on the inside of the wing. However, we don't have enough good data and enough good theory yet to have this all be backed by an analytical mathematic model. In other words, there's no perfect formula for how this camber versus lift versus everything else changes. So it's still empirical data. In other words, these airfoils are just tested in a tunnel of wind, and based on how much the wing is pulling up, they characterize these different lift forces. So when we're changing our angle of attack with our brakes, we're also changing this camber of the wing, meaning that there's a lot more at play here than a simple angle of attack change. Now, is that particularly important for most of you guys? Probably not. If you're wanting to really get into the math on the changes in your wing, I'd recommend not worrying about it as much. Instead, go out there and fly more, test different spots in your brake, use your flight instrument to look at your glide ratio, things like that. That's going to be a bit more helpful than trying to mathematically prove where the perfect brake position is. But anyway, I kind of got sidetracked there, so we'll talk a little bit more about this angle of attack. With this, there's a point, right, where you can imagine this lift force is almost perfectly vertical with only a little bit of thrust. That's what we usually refer to as minimum sync. So MinSync is this point in your brakes where you have the most lift force so that you're descending at the slowest rate. In other words, so what you can do with that is, let's say you're soaring along the south side of the point of the mountain, for example, and you hit some bumps that have some good lift in them. If you pull into minimum sync in those areas, you're now adding your wings' newly generated lift force, which is nice and steep here. You have a lot of lift there. You're adding that to the natural lift coming up the hillside from the ground. And you can imagine if we have more arrows going up, that means that we are going up faster. That's where that MinSync kind of comes into play. However, as you can see from our drawings, when we're at that MinSync point, this little thrust arrow here is a lot smaller. So what does that mean is, what that means is that our glide ratio changes significantly. Now we have all this lift force, but we're not moving forward. And if we're not moving forward at all, our glide ratio is going down to 0, meaning that we're not going to go very far we're not going forward, we're just descending slower. So this isn't like I'm going to fly in MinSync all the time so that I always have the most lift. The idea is that you're going to use that MinSync point a little bit more effectively in different parts of your flying, in different parts of your flight. Cool, so I mentioned glide ratio a couple times. For those of you who might not know yet, our glide ratio you can consider, don't know why I drew this backwards, but our path of flight, which is our dotted line here, our glide ratio, you can think about it as kind of our horizontal path compared to that vertical path, which it actually equates exactly the same as your lift over drag ratio. Those are going to be the two of the same things. And so basically with this glide ratio, that's what a lot of us as paragliders are trying to improve all the time. So if we can glide better, it means we can reach the next thermal higher up and therefore still catch that thermal. If we can glide better, we can glide farther. If we can fly farther, we can fly for longer. It just goes on and it's all good. So what does our angle of attack look like with our glide ratio? As we decrease our angle of attack, in other words, we're bringing that wing lower and lower. This is a very dramatized version of this, where let's say we're almost at a 0 angle of attack relative to our airflow here, right? Nice and steep, tiny little angle of attack in there. So what that means on our wing is that we look again at that lift force, right? Much smaller component that we see as lift as pilots under the wing, and much larger component that we see as that forward thrust. So as we go down an angle of attack and start reaching more of this looking wing, that means we're going to go up in speed. Now, it doesn't necessarily mean we're going to have a better glide ratio because we also have less lift. So what that means is that somewhere in between, let's call it max speed and min sync, there's going to be some key point where we're at the perfect glide ratio. And that's what we usually refer to by the polar curve. I'm sure a lot of the experienced pilots here have heard of the polar curve or try to use it to some capacity. But it's basically this plot where you compare your sync rate compared to your horizontal airspeed. And those all come down again to changes in angle of attack. And that ends up plotting into kind of a weird shape. And the main idea here is that if you want the perfect glide ratio, you're going to look at this line that goes from this 0 point and then touches this curve. And that's going to be your perfect glide ratio in theory. Now, again, good, great. You now know the math behind it. If any of you are pulling out charts and drawing things with rulers while you're up in the air to figure this out, send me a video of that because I'll be impressed. Not really realistic. So again, as paragliders, when we're out in the air, if you want to look for the best glide ratio, it's going to come down to a lot of trial and error on your specific gear because each wing's going to behave a little bit differently. So with that, I mean, if you really want to get into it, I'd say your best bet would be to go somewhere where you can either drive up to a launch or like Jackson Hole, where you can ride a ski lift up to launch. On a perfectly calm day, go out there and fly, play with a little bit of brake, play with a little bit of speed bar, and keep looking at the glide ratio on your flight instrument to start kind of figuring out where's that perfect point for if I'm just out on glide, this is where I'm going to get the farthest. Now, most modern gliders are designed with the intent that that glide ratio is at your trim speed. Used to be there was a little bit of speed bar necessary. I didn't mention this earlier. Speed bar is going to pull down your leading edge here, and that's what's going to give you that lower angle of attack. But anyways, earlier a lot of wings were designed so that a little bit of speed bar was necessary for your best glide ratio. Now most wings are designed with the intent that trim speed, so brakes out, speed bar off, should be your best glide ratio. I mean, this is changes in millimeters in line lengths, though. So if you took a huge whack on your leading edge, let's say, that might stretch out your A-lines just enough that now your glide ratio is no longer perfectly at your trim speed. So these things change a lot. Maybe that information is a little bit more than you need, but that's kind of the idea with that MinSync, best glide, all of that. So, cool. And then I want to talk a little about drag. Do you guys have any questions so far on this angle of attack stuff or anything from earlier? Feel free to chime in. All right. So a couple different types of drag. One is called parasitic drag. Parasitic drag. I believe this is also viscous drag or invasive drag. We'll stick with parasitic for right now. Basically, this parasitic drag is the drag that's caused by, having a big piece of material flying through the air. That's a very bad drawing of a paraglider. All of your lines are causing parasitic drag. You down here as the pilot is causing parasitic drag. Your harness is causing parasitic drag. It's everything that's pushing the fluid around. Think about just pushing your hand, palm out, through a bunch of water. What you feel on the surface of your hand is parasitic drag. Now the other type, called induced drag, and that's actually a totally different phenomenon I'll draw for you here. Let's say this is our paragliding wing and it's coming straight at us. We've got our pilot down here having a great old time. A few lines coming down. He's coming straight at us, right? As we talked about earlier, we have low pressure on the top. Those are negatives. On the bottom, we have high pressure, positives. And the whole idea behind our lift force is that our fluid wants to move from high pressure to low pressure, right? So throughout most of your wing here, that means that it's just kind of pushing up, maybe a little bit out. But around the tips of your wings, this is where things get interesting because now you have this opening gap out here. And so you actually see air pull around the sides, which actually results in these huge swirls coming out the back of your wing. And these would be left behind you. This is what's commonly known as, let's say, wing wake, vortex shedding, that sort of thing. You can also get wing wake off the trailing edge of your wing if you're deep in some breaks, but whole other matter. So in this case, your induced drag is a drag force generated from this inefficiency of kind of losing that vortex off the side of the wing. So the reason that you'd want to go with a really high span on your wing, in other words, it's if you were to look up left to right, the wing above your head would be a lot longer. It's going to mean that you have relatively smaller vortex shedding. In other words, you have a lot more of this area where you have lift forces pushing your wing up compared to these little swirls off the wingtips. So that's a big reason that like glider planes you'll see have a huge wingspan. They're looking for very small amounts of induced drag, and so that's part of that. You'll also see some paragliders model some of the Warriors and jet airliners. Specifically, I'm talking about advanced paragliders. And they have these little winglets coming out the tips out here. And the whole idea behind that is that these are going to generate a little swirl that's going to hit this other swirl coming off the tip. And those two should be destructive if they're rotating in opposite directions and just result in not having that vortex shedding, which results in less drag. I haven't seen any actual numbers or any math as to whether or not the winglets that Advance is using are actually effective, but the theory is definitely solid. I mean, that's you'll see that in jet airliners that have the kind of winglets coming off the back of the wing. Sometimes they're just pointed up. I think some of them, I don't remember who makes them, there's a second winglet coming down. This is the fuselage out here. I'm bad at drawing. We won't worry about that. So that's kind of your basic idea in the induced drag. And then One follow-up is that these two types of drag change depending on your speed. So as we move from left to right, we're increasing in speed. As we move from bottom to top, we're increasing in drag. So we'll call our parasitic drag, we'll call that our red drag here. It's going to be roughly linear most of the time. Might change a little bit toward the end. Parasitic. Cool. And then our induced drag we'll draw in blue here. And that's actually going to do the opposite thing, and it's not linear. This is induced. In other words, as we're flying faster, we see less of an effect from induced drag, but we see a larger effect from parasitic drag. So with those two things in mind, if we add these two drag forces together, we end up with this third line where right where these 2 points cross is going to be the low point on our total drag. So that would be kind of your best bet on your speed to fly. Again, in theory, that's going to be roughly at your trim speed. Now with parasitic drag being dependent on yourself, your harness, all your lines, you can see where that starts to play a different role, and that's why you'll see all your XC and your competition pilots in those pod harnesses that go around your legs and feet. Those are trying to be closer to an airfoil shape so that air can more easily split and move around the pilot. So with that, you have less parasitic drag, and therefore this point can, let's say, move to be a bit lower down here somewhere. Roughly the idea. Less drag means you can fly a little bit faster, you can be a little bit more efficient and use more lift effectively. Cool. So following up from that, I want to talk a little bit about stability in terms of pitch, roll, and yaw. And then I'm going to go into a little bit on your weight under your wing, kind of your G load, as well as some talk a little bit on stalls. Do you guys have any questions before I move forward with any of that? All right. Cool. So let's talk about stability. Not the right one. So unfortunately, there's like a few different different kind of uses of the word stability in paragliding. So what I'm going to be talking about is just when you are turning and maybe rolling a bit off axis, what that means. So again, we've got our paragliding wing here, leading edge right here in the front, cord right here, span going along the leading edge. We're going to talk about stability in three directions: pitch, roll, and yaw. So our pitch stability is going to be kind of rotating around this axis here. In other words, if you were to look up as you're flying, your wings moving forward or backward, that's pitch in this case. Cool. So why are we stable in pitch? Basic idea, we think about a grandfather clock, anything with a pendulum, right, where it rotates about some point up here, has some arm, and has some weight. That weight, if it's not straight up and down, is going to cause your pendulum to swing back and forth till it eventually reaches a resting position right down there on the bottom. Now if we imagine our paragliding wing up here, let's say it shot really far forward, we're the pilot out here, it's the same sort of situation. Now we're the weight that we saw earlier that's pulling down, that's us. And so we're going to swing forward a little bit, we're probably going to swing back a little bit, and then eventually we're going to settle underneath. So the whole idea with pitch stability is that if your wing surges or is behind you, on most A-wings and B-wings especially, without any input, you should return to that resting position. So this is what we teach a lot of our P2 students, specifically because inputting brakes without the proper timing, you can actually make some of those pendulum swings worse if you brake at the wrong point. If we're trying to fly efficiently, though, we do want to brake and stop these surges or let out on our brake as our wing's coming backward in order to allow it to get back overhead. The guy who wrote that book, Mastering Paragliding, he called it the golden rule that your wing and your pilot should always be flying at the same speed together. So that's kind of the idea there. If you have this pendulum moving back and forth, you're actually going to be losing a lot of your glide ratio efficiency most of the time. There are ways to do, I believe they call it porpoising. I don't really know much about it, but supposedly you can use some of this changes in pitch when you're in kind of a generally lifty scenario. I believe it helps you maintain a little bit. Don't try that without looking into it further, though, because it might be a little bit off. Cool. So we talked about pitch. Let's talk a little bit about roll. Color that one in blue. So roll is about this axis here. And if you were to look up, that would mean that your entire wing is moving to the left or to the right. You can think about what that's going to do to you is you're going to end up on your left side or on your right side. So that's generally weight shift is how we would induce a little bit of roll. As we shift our weight to one side and the wing will start to come over. Cool. The roll stability is going to be the same thing as up here. The only difference now is that we're looking at our wing now rather than moving forward like it was up here. Now our wing's coming straight at us. We're the pilot down here, just happy to be there. And again, there's some weight, means that we're going to roll to balance out. Now, same thing as before. If you're on that A-wing or B-wing, more than likely, just keep your weight centered. Don't do anything fancy with your brakes. That roll should stabilize out. However, if you want to mitigate that, if your wing starts rolling one way, you could weight shift the opposite way to try to keep that wing level and staying over your head. Another thing to think about with roll is that most of your turns should be initiated with weight shift, which means you're causing some roll before you really get into your turn. And as we talked about before with our lift force, if we're rolling out here like this, our lift force has now turned to this angle, which means it's already starting our turn for us. So you could complete a turn entirely just with weight shift to instill some roll. Cool. Finally, we've got our third axis that everyone's been waiting for, yaw, right up here on the top. So if we imagine yaw, if you look up at your wing as you're flying under it, that means that one tip is moving forward faster than the other tip, something like this. You can imagine if you're sitting in a swivel chair like I am, you're twisting in that swivel chair. That's yaw. And this one's a little bit more complicated. It does require just a little bit of an understanding on Vloading, which we haven't really talked about yet, but that's okay. The basic idea, let's look top down on our paraglider who's flying along. Our leading edge here, our tip, trailing edge out here, another tip. Our paraglider guy is now flying this way, leading edge. Cool. We're looking from the top. So if he's just flying along, he has equal loading everywhere across the surface of the wing. However, if some yaw is instilled, let's see what that looks like. Let's say now it's something like this, but our pilot underneath was still moving down in this direction. That means that we have all this force on the bottom surface of the wing on this tip. We have less force on the bottom surface on this tip that's farther forward. See if I can do that more fancy like that. Cool. And now our pilot down here Fortunately, doesn't want to be going at that angle that the wing's pointed at. He wants to be going forward. So now you have this force pushing on this surface of the wing. You have less on the bottom surface over here. In fact, you have a little bit of what could cause a bit of a deflation or collapse if there's too big of a yaw pushing on the outside of this other tip. So what happens with this G loading and how that comes into play is that when you have more weight or more G loading, the wing's trying to move faster. It's not going to change your glide ratio because you're also going to be sinking faster, but it is going to move faster. So now if we look at this more heavily G-loaded side, it's going to be trying to push forward, while this other side that has less G-load is not going to be pushing forward as much. So that's going to cause that wingtip that's farther back to push itself forward and kind of swing forward in front. So again, should kind of mitigate itself without too much user input. Now, if you wanted to, you could always be braking that side that's farther forward, but that's again something where if you mess up the timing on that, you could probably throw off a little bit of this yaw stability. Now, I talk about this because I have talked to pilots who have had this issue with yaw as they, like, let's say, approach a thermal. Maybe that wingtip that's going to hit a thermal is going to surge forward a little bit. So you're going to have some yaw going on. Personally, I've never actually noticed this happening. Outside of pulling some brake in to really pull one side of the wing back, I've never noticed just natural yaw go on my wing. So I'm not sure quite how common that is. So yeah, moral of the story here though, especially on your A wings and B wings that a lot of our new pilots are going to be on, is for all of this stuff, your wing's completely stable without user input, right? The only time that this becomes a bigger problem is when any of this pitching, rolling, or yawing gets really dramatic, which usually comes from too much input with the wrong timing on the pilot end. That's when you can see this pitch surge and your wing might surge way too far forward. You're going to run into other problems that we don't have to get into right now. Yeah, so that's a little bit about that control, or that stability. Speaking of control though, we talked a little bit about changing the angle of attack with the brakes. So what that's doing is pitching your wing backwards. If you instead lower the angle of attack with your speed bar, you're going to pitch the wing forward, right? Draw that out a little bit here. So if our wing's now moving this way, if we hit a little bit of speed bar, we're going to pull down on this leading edge, which is going to rotate the entire wing clockwise a little bit. And that's what's going to cause that wing to pitch forward. On the other hand, if we pull some brake out in the back, that's going to rotate our wing the other direction and cause that pitch to go backward. That's assuming that you're using both brakes together, doing a little bit of a uniform pull. For roll, we already talked about it's a lot of weight shift, so literally just putting all your weight on one side, one hip, or all your weight on the other. What that's going to do as the pilot is now flying straight at us again. Let's say he weight shift onto this side, so all of his weight is over on this side. That's going to pull these lines harder and allow these lines on the other side to release a little bit and move up. That's what's kind of instilling that roll. That weight shift is instilling that roll. Now, yaw is a more interesting thing, I think. Basically, because if we're looking from the top down now, our pilot's flying along, moving forward, and then let's say he pulls some brake over here on this side. Now the wing's going to start to turn, and it's going to want it to fly more in this direction, right? But our pilot, we'll draw him in purple, he's got momentum. In other words, he's got mass and he was moving in a direction, so he wants to continue to move in that direction. That means that he's going to move this way, right, as his wing's starting to turn to the pilot's left. What that's going to do is, again, it's similar to a weight shift. Now you're going to load these lines on this side of the wing more and instill some roll. So by just inputting brake, you actually end up doing quite a bit with your wing. If you want to do pure yaw, it's kind of tricky. I mean, you'd have to pull some brake and also weight shift a bit onto that side to come out with that perfectly flat turn. And even then, I don't know that it would be a perfectly flat turn, but maybe not the important message to take away here. So yaw, with one brake input, you're going to instill some yaw. As a result of that, you're going to have some roll. For some roll, it's really just some weight shift. That's, of course, going to also instill a bit of yaw as you come around your turn. And then pitch here is going to be managed with that speed bar and your brakes. Cool. I mentioned this a little bit already, but we talked about kind of your weight under your wing and how that relates to, or how that is your G loading, and how that relates to your speed. So basic idea is as you go up with your G load, you're also going to increase your speed, but you're also increasing your sink rate, which means that you're just maintaining your glide ratio more or less. There may be small nuances on different wings that have a slight change in glide ratio, but for the most part, it's maintained. In other words, if we're flying out on a calm day, it's not necessarily going to be beneficial to our glide ratio to have more weight. It might be beneficial if we're wanting to feel that full weight in the wing to prevent some smaller deflations, but it won't change our glide ratio. But when it will change our glide ratio a little bit is when we're looking at a headwind, because now as we're flying this way. If we have a headwind pushing us back, we want more speed to push forward. So if this headwind's strong enough and we aren't moving forward, then we're just sinking and we're just going straight down. You can imagine that's a pretty bad glide ratio. That would be 0. But if we weigh more on our wing and we just have more mass with us, maybe we carried water ballast or we put some rocks in our bag, now we actually are going to increase in speed. We might increase in sink rate too, but that increase in speed is going to be the only thing that allows us to penetrate. So now we have a glide ratio. So that's where you'll see a lot of pilots adding some ballast, adding some weight on a windy day. That way they can penetrate into that headwind quite a bit better. Cool. Now, bigger things to consider with G loading is it's not always going to be about just the weight that you carry with you. The big issue is when you get into deep spirals. You'll also notice that G loading if you're in a really big, you have a lot of lift from, let's say, a big gust in your ridge lift or you hit a thermal, you'll feel that kind of sinking feeling in your gut as you get pulled up. And that's that G loading. But in spirals specifically, as you get deeper and deeper into that spiral and you're turning around and around and around and around, basically what's going on with that is your wing is turning at this pretty steep angle and you are then swinging around the center point, which means you have a centrifugal force that's pulling you out, or that you feel pulling you out. And that G-force, while it loads your wing well, meaning that it won't have these little tiny deflations as likely, it also means that blood is not getting to your head as easily, and so that's when you can start to get dizzy and get lightheaded, and that can lead to you passing out. If you pass out in the air, I'm sure I don't have to tell you that's a very bad thing. So when you start to feel dizzy and you start to feel this G loading, it's just important to really be considerate of it. And I mean, if you're in a situation where you're turning, you're starting to feel a little bit lightheaded and you can get out of it, great. If you don't know how to exit a deep spiral, though, that might be time to throw your reserve, because if you don't throw and then you pass out, it's too late to throw. Cool. So I've got on G loading, a little bit on stalls, what they are, what they look like. The easiest way for me to talk about stalls is to start by talking about kind of general airplane stalls, what those look like. So our wing's flying along. We're an airplane now, so it's flying horizontally. As it does so, this fluid is moving. We draw that this air is just moving nice and easy along the wing. Not too many big issues. Everything looks clean and laminar. That's what that laminar airflow means, is that basically a particle of air is just kind of following these nice, easy lines. Now, as we increase our angle of attack, eventually we reach this point where that's no longer possible. As I mentioned earlier when we were talking about the CoWanda effect, where we had that shelf that dropped off, we saw airflow separate. You know what that looks like? A lot of our air doesn't really look much different. But we do see a change right in here, where this is kind of that separation zone. So in this case, the general airflow has left the wing, meaning that the particles of air in this little area are following along with the wing. But air is viscous, meaning that, like, let's say, honey or any other fluid, if you move part of it, the fluid nearby also moves. It's basically a friction force is the way to think about it. And so because we have this airflow on top of this stalled region, or this flow separated region, we have no airflow inside. That means that we're going to start to see some rotation, and that rotation is turbulence. So with that, on a rigid wing on an airplane, that's going to be where you no longer see a lift force, as we're losing all the lift force across the back of our wing is where it usually starts and then propagates forward. And that's when, in a full stall, you'll end up seeing these airplanes lose all that lift force, start to fall, and then they'll pitch down into a nosedive, and that's where they can regain speed. They regain laminar airflow over the surface of the wing, and they kind of swoop out to finish out that recovery from stall maneuver. Now, the start of a stall in a paraglider is exactly the same. It looks just like this. What's different on our wings is that they're not rigid, they're completely flexible and collapsible. So once we get into this point of stall, which is granted usually pretty deep in the brakes, pretty steep angle of attack because we're at such low speeds, once we start to see that stall though, now I'll just draw on this one. We have our cell openings on the front here. Now we don't have the same kind of pressure differences that we had before, so it's easy for this air to get actually pushed forward inside the wing. I'll draw that in green, which means it's escaping out the front of the wing, and if air is escaping the wing, it's collapsing, right? So that's when you'll end up seeing this wing kind of go into this collapsed shape, and eventually there'll just be this ball of a wing up above the pilot. So recovering from that is not something that you should practice on your own. It's something you should learn in an SIV, where you're over a lake, you've got an instructor on radio. Recovering from these full stalls can be pretty violent. And so in order to do that, you want somebody who can kind of explain to you step by step what's going on and what you should be doing as the pilot with your brakes. Because if you just go hands up in this case, that wing maybe will reinflate fine, but then it'll surge all the way forward and likely all the way down, which is not what you want. We don't want to be above our wings. Cool, so this is full stall. Full stall. Now, there's also a point on our paragliders that's just before this point of full stall, where we still have a little bit of flow separation, especially maybe right back here on the back, but we don't have enough that it collapses the wing entirely. We call that a deep stall or a parachutal stall. You'll hear it called parachutal stall a lot. And that'll basically look like you're flying along and then you suddenly realize that you're sinking and you have no forward speed on a non-windy day. And that can be dangerous. For one, you're really close to this full stall point, which is pretty difficult to recover from. But for another, if you're in that deep stall and you want to get out of it and you just let your hands up, you're going to have this huge surge as the wing tries to reinflate and surge forward, which can get dangerous. You can, again, get up above your wing, not what you want. So getting out of that deep stall should be a slow process with your brakes. I don't have any like great pictures to draw for that because it's roughly the same scenario, just not quite to the deep, not quite to the full stall point. But yeah, so when you start noticing that your ground speed is going next to zero, if you start feeling more like you're dropping than you do like you're flying, that's when you want to look up at that wing and see, like, man, how deep in my brakes am I? Am I down below my carabiners? Should I be concerned? And be ready to come out of those brakes slowly so that your wing can slowly reinflate and slowly regain speed with you. If your wing reinflates and regains all its speed before you've regained your speed, that's when your wing surges. Cool. The last thing I've got on here, and I'm not totally sure it's completely applicable to aerodynamics, but we're going to cover it, is the wind gradient. So along the ground, there's trees, grass, houses, whatever. As far as the air is concerned, there's friction. And as we move up away from the ground, there's less friction. So if we check our wind today and we know it's going to be 15 miles an hour, we know we're going to have a slow approach on our landing. But that friction is going to slow the air way down right when it's down here close to the ground. It's going to exponentially increase in speed until it reaches kind of our steady state speed, if you will, something kind of like this. So as the pilot out here, you might be flying along up here, working against this headwind at a pretty low forward speed, right? Throw that in purple. But as we get closer and closer to the ground, that's when we might notice that our speed doesn't have that same headwind to contend with, and so now you're moving a lot faster. Now, a common mistake on a lot of early pilots is you notice that your speed suddenly increasing, you try to slow down as you come in close to the ground. Now, while that might help you maintain your speed that you had up higher, that means that when you go in to do your final flare, which is what kind of cups your wing and allows you to stop and then plop down nice and gently, you can't really get a good flare if your hands are already down below your chest or lower, because you don't have as much of a wing to grab and pull back. So with that, kind of the important thing to note is that as you're coming in toward landing, your path is going to be coming down. Your path might be coming down at the same rate for a while, but then as you get closer and closer to the ground, you might speed up quite a bit and see that you're overshooting a lot of your landing areas. That's why that wind gradient is pretty important. And then while we're talking about wind, we may as well do a little bit more vector math here and look at how things change with our airspeed. What's called blue our airspeed. So this is the speed that our wing flies through the air. You might notice that on pretty much any wing you can buy, you can look at the trim speed. That's considered your airspeed. Breaks out how fast is the wing flying. And that doesn't change because if there's a headwind, your airspeed is relative to the air. And so that wind is moving at you. But if we imagine moving along with the air, we'd still see that paraglider moving through it at the same speed regardless. So if we had whatever airspeed, let's say it's 18 miles an hour, let's call it 20. We had no headwind, no tailwind. We could expect our ground speed that I'll draw here in green to also be 20 miles an hour. However, if we had, let's say, a 5 mile an hour headwind come in, our airspeed would now be 20 miles an hour because, again, airspeed isn't dependent on that wind, but our ground speed, so how fast we're covering the ground, that's what would get pushed down to 15 miles an hour. And similarly, if we had a 10 mile an hour tailwind, our ground speed, 20 miles an, or air speed, 20 miles an hour, but our ground speed would now move up to 30. Just a couple quick considerations on different wind speeds and kind of how that affects your wing. The main thing is that wind isn't so much affecting our wing as much as it's affecting our ground speed. Cool. So with that, that covers everything I've got written down here. Certainly can go into more detail on anything, or if you guys have any other questions on some of this aerodynamic stuff, I'm happy to get into it with you.
Ryan, I'm fairly familiar with parasitic drag. Could you go over again the other drag?
Yeah, induced drag.
Induced drag.
Yeah. So basically, let's see. I'll try all my artistic skills on this one. So we've got our paraglider, which I didn't want to draw in green. So we've got a paraglider here. Our leading edge up in front there. Our trailing edge kind of in the back. So we talked a bit about the low pressure region on the top of the wing, right? That helps produce lift. Those should be minuses. This is all low pressure. Underneath the wing, we have this high pressure. Again, due to that turning of the airflow. And normally we're moving forward, which means that we don't see air wrapping over the leading edge here in the front. So instead we see air trying to push against the bottom surface of the wing and wrapping back a little bit on the trailing edge, but not a lot. That's kind of some of that wing wake that we talked about. But out here on the wing tips, that's where we see, okay, now our air can actually escape around the side of the wing. As it does so, it leaves this high pressure region and then gets sucked into this low pressure region, creating this little bit of a turn. And as this wing is flying forward this direction, right? As the wing's flying forward, it's leaving this rotating air behind, meaning that it's starting to turn, and then it's just kind of like still has its rotation rate, but it's being left behind from the wing that's moving forward. Now how specifically does that cause drag? I mean, that's kind of another issue altogether, but my understanding on it is basically that induced rotation is actually kind of causing a pull back on your wing. I don't know if that clears much up for you, Neil.
Thank you.
Yeah.
I mean, we talk about parasitic drag all the time, and our lines and our bodies and our flying through the air, but we just don't seem to talk about
this induced drag. Yeah.
Induced drag very much. So I was kind of, I mean, I get it that it's swirling. It's funny because I do fly an advanced wing, but I think those tips are purely for show and marketing.
Yeah. I think that so I mean, they advertise that they help with this induced drag. And I'm sure that, like, if you were to run numbers, technically you would notice that by the numbers, there's less induced drag on those advanced wings with the wingtips. But I mean, they're so small, and I'd be shocked if they were a substantial change. The reason we talk a lot more about that parasitic drag, though, right, is that comes down to like the line layout of our wing. That comes down to what we carry with us as a pilot down here. You can imagine that if I'm in some bulky sit-down harness, the air can hit all this surface, and none of it's very aerodynamically shaped. But if we look at our pod harnesses, and they have more of that type of shape. I'm going to see how to draw this so it makes sense. I'll do the pilot in here in kind of banana shape. So this is closer to a streamlined body, which is, you can imagine kind of the top surface and bottom surface of a paragliding wing. Air can move over and around this really easily. It's going to be the same thing around one of these pod harnesses where air can really easily move around it. On the other hand, if we're in here as our little pilot, doing our thing, right? So now air can hit us and start to move around us, but off the back side there, it's going to be a lot like those little stall pictures I was drawing, where that airflow actually separates before it comes back together. And so those little stall points cause a lot of drag behind you. That's why you'll see a lot of research going into these pod harnesses. Now, what I think is interesting, if you've flown down in...
Considered induced drag?
What's that?
Would that also be considered induced drag in that case?
So that's parasitic. Induced drag is just from this...
Okay, so you're not creating a vertice behind you. You said when it separated and then came back together, I figured that separation was then...
It's not quite the same. I mean, this vortex that's shedding here, that can be a totally laminar airflow that just has some rotation, which is interesting. When it becomes turbulent is when it's more of a stall. In that turbulence, I mean, we draw these little swirls, but it's completely chaotic. It's, I mean, imagine one way to look at this is if you had like a big pot of soup, let's say, and you were churning it up with your spoon, right? As you keep moving it at the same rate with your spoon and you're rotating that whole thing, you're going to see whatever you've got. Let's say there's rice in there. You'll see the little bits of rice moving around in a circle. Now, that would be a lot like this vortex shedding, where you can see this like laminar rotation. On the other hand, if you're still turning like that, and then you suddenly just change direction really sharply and kind of rip your hand around through the flow you've generated, now you're going to see all this chaotic swirls happening and hitting each other and breaking apart. And that's more what our turbulence looks like. And that's what's going on behind this pilot, or behind the trailing edge of a stall. Yeah. Yeah. Now, you might also have a little bit of this parasitic drag on the pilot himself, but less likely, and kind of depends where that would be.
I mean, you do really notice it. I mean, going down from a 4-line riser to a 3-line riser, I could tell myself that I could feel it myself that the drag was less, and I can only imagine what those 2-liners are like since I don't fly them yet.
Right, yeah. Well, I noticed that too. I mean, I've been flying a low B-wing for years and years, and just last spring got a pod harness for it and just like instantly noticed it's like, man, I'm flying faster. It feels better. Like you can feel these changes in induced drag for sure. One thing that I think is interesting, since I was talking about the pods a little bit, if you've ever flown in Valle de Bravo or at the, is it the Spring Fling out in Florida? But anyways, if you've flown with Cuervo, he used to be a hang glider pilot, now primarily paraglider pilot. He's custom built this pod harness so he can sit kind of what you're seeing here, but then he can also turn around forward to lay prone. And so the reason behind that is your streamlined body is more of this shape in the airflow that's coming at it this way. That's going to be the easiest way for air to pass around this body without allowing for any kind of stall point in the back. And you'll notice that with this, you have most of your mass out here in the front. So while in our pod harness, we've got most of our mass back here, most of our kind of size back here toward the back. This idea of being able to rotate forward means that he's now in this position where he's got his arms coming out here, and he's actually forward. Most of his mass is in the front here, and then his legs come out the back. Just thought it was cool when he mentioned that it's more aerodynamically efficient. It took some thinking, and I was like, holy cow, I can't imagine. I mean, imagine on the last leg of a big race, and the guy next to you suddenly rotates forward and then passes you. I mean, just fun, crazy stuff. So this is where aerodynamics can be important, as if you're wanting to do something ridiculous like Larvo.
Ryan, John had a question about skywalk jet flaps.
Skywalk jet flaps, yeah. So the idea behind those, those of you guys who haven't seen them, on Skywalk's wings, back here on the back, they have actual holes. And you could put your entire hand like through your paraglider. Now these also have material kind of around the hole, so you couldn't get into the cell openings on the wing, but you could go through leading edge to trailing edge. The idea behind that actually comes from airplanes coming into land. So you've probably noticed, especially on takeoff, if you're sitting on a window seat next to the wing of an airplane, the normal airplane shape, again, is that airfoil that we've been drawing. But as it's on takeoff and on land, it's got actual sections to it here. The leading edge comes down and the trailing edge comes down, usually in a few sections like that. And the whole idea on landing is that as air is getting pushed down, you're generating more lift force, you're pulling back that thrust, you're changing your angle of attack a bit. But where this particular scenario, I mean, you can imagine this should be a stall point right there. However, since we have openings in between these flaps, airflow can actually go through there. Roughly, that's my understanding of how this goes. So you're now looking at like 3 little airfoils there that all kind of reduce that ability for a stall point. So on that Skywalk jet flap, it's got that hole through the back of the wing somewhere back in here. So as you get deep and deep and deep into these brakes, your stall point should end up being at a much higher angle of attack, because now airflow can come through here and kind of destroy that separation in the back, because it allows air to kind of reconnect. Do they work or not? Everyone I've talked to says no, but no one I've talked to knows how they are supposed to work, so I don't know. John, you just picked up that Skywalk, so I guess you could find out how deep your stall point is over the lake sometime and let us all know.
I'm hoping for the